The key ideas for this lecture are mentioned here, which is a plot. We're going to figure out what those terms mean, G and R, as we go through. This is covered in 8.7 in Fogler. This is called multiple steady states. So you'll see that's what 8.7 is labeled. And this is the last part that you need for homework problem 6.6. So 6.6 is doing exactly the example that we're doing here. I'm going to sketch what the results look like. You'll just have to do them quantitatively. But these are basically the selected answers for problem 6.6. So a bit of recall from last lecture, from lecture 17. So as I mentioned before, I'm going to use exactly the same example. If you look in your notes, this should be exactly what we wrote on Wednesday, so you probably don't need to rewrite all of this. But I've summarized it here. I tried to pick all of these numbers to make them about as straightforward as possible, right? There's not really very much happening in this that initially looks interesting. It's an irreversible reaction, A goes to B. It follows an elementary rate law. The rate law follows an Arrhenius expression like we've seen before. The heat capacities are constant. You can't get much better than that for heat capacities. And we have this would be a submerged heat exchanger, the coiled kind, which is that glass one that's floating around. And then we're feeding in pure A at a certain volumetric flow rate. So there's nothing really hiding in terms of interesting things that happen due to a particularly complex reaction or complex reaction kinetics. And yet, as we saw, or at least I had mentioned on Wednesday's class, we find that X for here, for this particular reaction, was not one value, but several values. So I think I said it was 0.5%, or it could be 38.5%, or it could be 96.8%. And so our goal for today is figure out where do those numbers come from? How come we have multiple conversions? And do they mean anything? Are they physically possible if I have a reactor sitting in front of me that looks like this? How do I choose which one the reactor is going to work at? Can I actually make the reactor work at all three of those, even though they're physically possible? So the first step of how do we come up with these numbers is more straightforward than how do we interpret them. The way that we come up with them is we solve the energy balance. So the energy balance that we have for a CSTR, we saw this before, it's the amount of Q that you're taking in or out, so UA times T minus TA, minus UA times T minus TA. And then we subtract off all of the enthalpy terms, so we have FA naught times, actually I think last time, you could put that inside, but I put it outside before, so to be consistent, times the sum of theta I CPI times T minus TI naught. Actually, I had a good question in office hours today. Can I take this T minus TI naught out? Can I take it outside of that sum? Depends on what?
If all your species has the same inlet temperature.
Yes, so it depends on whether or not everything's got this same TI naught parameter here, the inlet temperature. If everything's coming in a single stream, then they've all got the same inlet temperature, and you can move that out such that the sum just looks like sum of theta I CPI. We write it this way generally because we have multiple inlets going to our system, so this takes care of multiple inlets. And then we had our reaction term, which was, I'm going to put underneath here, minus FA naught times XA times delta H. And we had two different ways to write that FA naught XA delta H term, depending on how you want to represent FA naught delta, or sorry, FA naught XA. From our material balance, we can write FA naught times X, whoa, what happened there? FA naught times XA, that's an FA, FA naught, times XA is equal to minus V, that's capital V, which is our reactor volume, times RA. So we didn't need anything from the energy balance with that. If we also know that minus RA is equal to K this is the lowercase k, right? We don't have equilibrium. I'm going to carry around k of t just to remind us the whole time that k is a function of t. But we're not multiplying by temperature. I'm just indicating that don't forget k is a function of t. So Ra is equal to k times Ca. Ca is going to be Ca naught times 1 minus x. So we combine our material balance with our rate law, and we can determine that our x sub a, so here again I'm going to be explicit and mention that x sub a is a function of temperature. If you plug all of this in and rearrange, you'll get something that looks like this. To the minus 1. So 1 plus V naught. V naught there is the inlet volumetric flow rate. Capital V is the volume. Divided by kT, that whole thing to the minus 1. Where did that V naught come from? Where did this come from? CA naught and an FA naught, right? There was a CA naught here and an FA naught here, so I got rid of those and used V naught instead. So it didn't appear anywhere particularly mysteriously. But we don't have enough, right? We need to figure out what the k value is, for starters. So k at any value t is equal to k at some reference value t times exponential, I'm going to run out of room, minus EA over R, no, I'm going to squeeze it in there, 1 over T minus 1 over, what was our reference temperature? 300. Right, so we use an Arrhenius expression to get K. So that's better, right? If we knew what temperature was, we could presumably calculate X, but we don't know what temperature is. In order to get the temperature, we're going to have to put this into the energy balance. So the version of the energy balance we would end up looking at is minus UA T minus TA. That didn't change. Minus FA naught times CPA. We can get rid of that sum there because we've only got one thing coming in. There's nothing else coming in. So now we've got T minus TI naught minus FA naught delta H, and now I'm going to plug in my expression for X. So my expression for X was 1 plus little v naught divided by capital B, V volume, times K of T. All of that to the minus 1. I hear mumbling. Did I forget a negative sign somewhere?
I think we're just passing around the reactor.
It is pretty neat. I kind of dig it. I could pass around the other reactor, but it's literally a glass bell jar, so there's not much to see there. So now it becomes a question of, do I have enough information to solve something like this? So you have a question on your homework 6 that says, show that you have enough information to solve something. One way to do that is to look at the number of equations I have and circle all the unknowns that you have. If you have a number of unknowns equal to the number of equations, digging back from your CENG 100 days, then you have enough information to solve it. Whether or not you can is a different matter. It can be a very difficult problem to solve, but you can show that there is a solution to it. So if I look through this expression, let's see, I know U is good, A is good, but T is not. I don't know T. TA is okay, because I know what that is. It was given to us. FA naught and CPA are both constants. TI naught was also given, but here I'm missing this T as well. Continuing on, FA naught was given, delta H was given, both of which are constant. I know 1, hopefully. I know V naught, not a problem, that was also given. I know the volume. I can figure out what K of T is, right? I kind of know what K of T is if I knew what T was, so I could say, yeah, I know what K is if I know what T is. So I kind of know what k is. I still need to figure out what t is, but once I know t, then I can get k. And then presumably you know how to do -1 to an exponent. So I have one unknown and one equation. So presumably there is some way to solve this particular equation. I could drop it into my calculator. It would probably be able to solve something like that. I could drop it into MATLAB or Excel. The problem is when you figure out what the solution is, you might not get a single result. The reason you won't get a single result is most easily illustrated if you evaluate this entire expression for many different temperatures. So for example, if I rewrite this, I know that I have 0 is equal to, I got to pick a letter we haven't used yet. Do we have a lowercase h anywhere? We have an uppercase h. Some function h of t, where h of t is all that stuff that we did up here. Right? So just represent that entire function. Everything on the right-hand side is a function of only the variable t. So if I plot h of t over many different t's and figure out where does that thing cross the x-axis, I'll know those are a potential solution. If you plot something, who took my CENG 15 class? Remember plotting F0 and all that stuff? And I said you had to plot it first. This is why. I love this. If you plot that, 15 years of chemical engineering will do stuff to you. If you plot that and you say here's t and here's h of t, and I'm going to illustrate 0 as right down the center, what you will find is that h of t does something like this. Actually, I don't know that h of t does something like that. Qualitatively, it will do something like this in the sense that it has crossed the 0 3 times. It crossed once here, and once here. If you evaluate each one of those crosses, again, I don't know if this h of t curve looks like that, but I know where it crosses, which is this. You'll find that it crosses at a couple different temperatures. One of them is 327, one of them is 442, and one of them is 618. There's usually no way to figure that out unless you actually plot the function. Most solvers, unless you're using a symbolic algebra system, most solvers that rely on numerical iteration can't find these multiple solutions unless you tell them approximately where those solutions are. How do you know where the solutions are? You plot them. And there's several different ways that you can tell it to solve for which one you want. You can also just look at the graph and approximate what that temperature is, right? If you can approximate to within maybe 1 degree Kelvin or so, that'll probably be enough for the purposes of our homework at any rate. Usually if you're within about 1 degree Kelvin, that's okay. Yeah?
Can you use a global optimization tool?
If your global optimization tool can find all of your zeros, but this isn't really an optimization problem because there is no global minimum here, that's what we want. The global minimums here would be something that doesn't satisfy the energy balance. So it becomes a question of how do we figure out which one of those temperatures is the one that we're actually going to function at. Once we know what any of those temperatures are, we don't have a problem calculating what the corresponding conversions are, right? Earlier we saw that the material balance ends up looking like 1 plus little v naught over capital V times k of t to the -1. So if I put my temperatures in here, the output will be the x that corresponds to whatever that temperature is. So if I plug in each one of those, that's where those values are coming from. One of them was 0.5%, 0.5%, 38.5%, and 96.8%. So that's the mathematical portion, right? If you just want to know what are the solutions, this will tell you what the solutions are. But it doesn't give you very much information about which of those solutions is the one that A, we might want, or B, the ones that we can't reasonably operate at, or C, how do we get from one of those to the other if I actually have a reactor sitting in front of me and I can adjust something. In order to do that, we're going to employ not a dirty trick, but it's kind of a trick. Instead of doing this, instead of h of t here, we know when h of t is equal to 0, we have solved the energy balance, right? We have satisfied the energy balance because we have a 0 on the right and a 0 on the left. That means that equation has been satisfied. Instead of looking at h of t, we're going to split that equation into two different parts. The two different parts correspond to something that's physically happening in the system, and we can learn something from those. So previously, you should have had this equation up here at the top. And we're going to do the following. We're going to call this entire term, everything from the Q term all the way over to the end of the sum term. We're going to give that a special name, and we're going to call that R. Capital R, and keep in mind that R is a function of temperature. The other term that we're going to come up with is this term down here that has something to do with the reaction. The whole FA naught XA term. We're going to call that G. And keep in mind that that is also a function of temperature. Why is G of T a function of temperature? Because X is a function of temperature. We use the material balance to show us that X is a function of temperature. And in a more general case, delta H is also a function of temperature. Why do we say R and G? R is generally understood as the amount of energy that we are removing from the system. It's either going to heat up the other elements inside there, or it's actually being taken out through, for example, the walls of the heat exchanger like that, or through that, where's my glass one? Through the coils inside the glass one, if your heat exchanger is submerged. So R of T conceptually represents where is that energy going. It can only go in one of two places. It can either go to heat everything up, like we saw with the stars, or it can go into whatever your jacketed fluid is that's cooling everything down, or potentially heating it up if you have an endothermic reaction. So R of T generally stands for the amount of energy removed. That R being why we call it R. G of T is just the opposite. It means where's the energy coming from? We are generating some amount of energy because we have a reaction. That reaction is giving off energy through its enthalpy of reaction. So there's not too much to talk about in terms of G, other than that is approximately what we mean when we say G, which is this is the amount of energy generated. We're playing kind of fast and loose there with generated and consumed, right? Energy is never created or destroyed, it just changes its location. So when we say generated, we're kind of hand-waving when we mean generated energy. You can't generate energy except in the sense that a reaction gives off energy through the enthalpy of reaction. So we have these two terms instead, and what we're going to look at is not when does R plus G or R minus G equal to 0, but when so our general expression now looks like 0 is equal to R of T. You can play with the signs however you want to make this work out. Minus G of T. Generally, what we're looking for is when does R of T equal G of T. If you are removing energy at the same rate at which the reaction is releasing energy, you must be at one of the steady states that we can do. This is an alternate way to solve exactly the same problem. You can either do what we did here with H being the full term that we have down here on the bottom, right? If you just want to know where the numbers are, you can dump it into something that looks like this, but it's not particularly illustrative of what's happening inside the system. Instead, if you split them into R and G and you equate R and G, as we've done here, Whenever R and G are the same, we are now at steady state. So this becomes our version of an energy balance for a CSTR. If you look through your book has some pretty complex expressions for R of t. The reason that those, or sorry, R of t and G of t. The reasons those expressions look so complicated is because they're making assumptions and saying if your system follows a particular pattern, or your H follows a particular pattern or something like that, then you can get an explicit equation for R of t and G of t. I tend to think it gets a little bit confusing if you present those complicated expressions, because now you're going to look at those and say, I have to make my system look like this. Generally, R and T and G of T are just talking about what shows up on either side of that energy balance. It takes certain forms depending on what your system looks like, but we're not going to explore what those forms look like because they're just simplifications of this general expression that we've got up here. And also, we don't have to introduce any new variables because I can just leave it in terms of that. Your book introduces, I think, 2 new variables, including yet another k, and it's hard enough for me to draw 2 k's, let alone 3. If we can get R of t equal to G of t, then we will know that we have a solution. So we can make the same kind of plot that we had here, except instead of plotting H of t, we're going to put R of t and G of t on the same axis. And we're going to try to find out where those points intersect. So give yourself, I think I drew this on my notes here. If you hold out your thumb, make sure your axis is about as big as your thumb. I'm going to draw it really big on here because we're going to annotate the crap out of this plot. So give yourself plenty of room to write on your plot. I know, right? I'm getting excited about plots, and you're all sitting there and you're like, I don't, it's just a plot. Oh, it's got to be a straight line too. Wait, I have a straight line. All right, so give yourself a nice big old plot on here. On the bottom is going to be temperature. And of course we're going to, oh, my line thickness there is not great, but we're going to go with it. Is still T as a function of K. And now we're going to draw 2 different curves. The y-axis is going to be either one of these. It's either going to be the amount of energy generated, G of T, or we're going to plot R of T. Yeah.
When you say T of K, does that mean temperature in kelvins? Or?
Oh, yes, I'm sorry. Yes, this is temperature in kelvins. You could do it actually in degrees Celsius if you wanted to. It would just take the whole thing and shift it. All right, now don't draw this curve until I try it a few times because I usually screw it up at least once. So let me get the shape right, and then you can work on getting the shape similar. Your G of T curve will generally not be a straight line. The reason that it won't be a straight line is because G of T is drawing on, I'm going to circle this, it's drawing on what you know about X of A, or sorry, X sub A. X sub A is drawing on K of T, and K of T depends on temperature as an exponential. So G of T depends on X, X depends on K, and K depends on the exponential of temperature. Whether or not you want to scramble up your notes. Wow, that's a really good looking sign. I like that. Anyway, G of T is not linear. It's usually not going to be a straight line unless you happen to be looking at it on a particular scale. So G of T typically has a curvy S shape to it. And I'm going to try to draw this about maybe 1 or 2 times. Oh, I got it right first time. Draw a curve that looks kind of like that. This is what G of T usually looks like. Oddly enough, no matter how complicated your system is, it usually ends up looking like that. It might shift, maybe, I'll just draw a couple of sketches over here. It could be very sharp, like this. It could be very drawn out, like that. If you have a drawn out system like this and you restrict your temperature to just a very narrow range, then it looks like it's a straight line. So where that waviness appears may be in a situation that's non-physical, right? If you have to get out to the temperature of the core of the sun before you see the waviness, you're probably never going to encounter something like this. But there are nevertheless reactions that operate such that a reasonable selection of temperatures down here, ones that I can actually operate, result in a G of T curve that looks something like that. If you want to know what those reactions are, dig up this section in Fogler, and it will show you a set of experimental data that got published, it's like back in the 50s or something, that demonstrated exactly this effect. R of T is a little bit simpler. If we look at R of T, the only assumption that we need to make on here is that R of T depends linearly on temperature. In order to get a linear dependence on temperature, we have to look at what in here could potentially vary with temperature inside our R of T term. So U is technically a function of temperature, but it's a very weak function of temperature, so we typically ignore it. That would be something that you would observe in 101B. You could figure out how U depends on temperature, but it's a pretty weak effect, so we're going to ignore it and say that that's constant. Area is typically constant. What area am I talking about? Actually, I have an example. If you have that glass one, the area would be the surface area of that glass tube, which doesn't change. If I have a jacketed reactor like this, the area would be the inside of one of these multiplied by 2, so two of them. So obviously that area also does not change. So area is constant. Inlet temperature of the coolant is, our base assumption when we were deriving all this was that the coolant temperature never changes. There are ways to ensure that that can be the case. We're just not going to go into them. FA naught's not changing because that's our feed. Theta is also not changing because that's our feed. Here's the last assumption. CP could be a function of temperature. We know that it's a fourth order polynomial function of temperature, but we also know that under reasonable circumstances, it doesn't change a lot over temperature. And in fact, very often we've been making the assumption that CP is going to be constant. We might have to pick which temperature we're evaluating it at, but we're going to say once we have CP, it's not going to change, which is not a terrible approximation. And then I guess the last one is Ti naught over here. The inlet temperature is also going to be assumed not to change. If none of those things change, then R of T is a linear function of temperature. There's no squared terms or square root terms or exponentials or anything like that of temperature. It's always temperature raised to the power of 1, which means it's going to be a straight line. This is the interesting part. The straight line will cross through that red line in 3 different places if you are operating in the way that we described. This is another one where I'm going to try to sketch it. I might have to do this. Oh, I have a line. Hang on, I'm going to draw an actual straight line to make this work. Here we go. Nope, didn't work. There we go. Come on, you got it? You got it? Bam. It's the wrong color. It's the wrong color. You can go ahead and draw that line if you want. I'm going to try and get the color right. Oh, there we go. Okay, all right, one more time, one more time. Bam. Oh, that's so satisfying. Okay, so we have an R of T curve and we have a G of T curve. If I had more time, I would go back and set the thickness of those lines to be the same, because they're obviously not. You think I'm joking, I really would. These 3 intersections that we have here correspond to the same temperatures that we saw before. Right, so if I were to evaluate those temperatures, I would get temperatures of 327. This one up here, if I look at what that intersection is, I think the other one was 442. And if I look up here, this temperature is the last one, which was 618. Or thereabouts. Right, there's maybe a little plus or minus 1 degree Kelvin. When you actually solve this on your own, you can figure that out to as many decimal points as you want. Right, and those are the same temperatures that we would get if we used H of T like this. But the curves look a little bit different, right? Now I'm looking for the intersection between 2 curves rather than the intersection of one curve with a 0, with a x-axis. But nevertheless, conceptually, those intersections represent the same point. It means you've picked a temperature such that G of T is equal to R of T, and therefore the energy balance has been satisfied. These are what are called multiple steady states. You can operate at any one of those. So the green points are multiple steady states. Each one of them individually represents a steady state at which the reactor can operate. We're going to figure out how to determine which one of those I want to operate at in a minute, but it's at this point the real power of G of T and R of T is that they will tell you which one you are going to operate at. The reason that they will tell you which one to operate at is because of conceptually what G of T and R of T represents. G of T represents I am giving off energy, I am generating energy. R of T means I am removing that energy somewhere. Typically it's going through the walls or something like that. And it's a balancing act, right? If you go outside and you run around and the temperature outside is 100 degrees Fahrenheit today, typically you're going to be generating a certain amount of energy and the environment is not going to take that energy away at a particularly fast rate. If it's not taking that energy away at a particularly fast rate, what happens to the temperature of you? If you run around when it's 100 degrees outside, you get hot or cold? You get pretty hot. If it is freezing outside, if it's 32 Fahrenheit, and you run around at the same way that you did when it was 100, now you're going to get cold because you're essentially giving off the same amount of energy, but the environment is changing. So sometimes the amount of energy being removed by the environment is greater than the amount of energy being generated by a reaction. Actually, that's a really good analogy because that energy is coming from a chemical reaction. I love it when science works out. That is a perfectly apt analogy. Your surface area, in that case, would be the surface area of your body that's getting rid of energy to the environment. So it becomes a question then of whenever I have a particular temperature of a reactor, which one of those steady states am I going to get to? For example, let's assume that the temperature of the reactor was right here. So call it, I don't know, 400. Somewhere in between the two. If I am at 400, keep in mind that this is my G of T and this is my R of T. Which one is bigger at 400 K? The rate of removal R or the rate of generation G? R, right? So if I sit down here, I have R. I'm going to do this in black. R is greater than G. If R is greater than G, generally speaking, is the reactor heating up or cooling down? It's cooling down, right? I am removing energy faster than it's being produced by the reaction. Therefore, I am going to tend to slide along both of these curves until I get to that lower steady state. So if somehow I just very quickly heat the whole reactor up to 400 K, and then take away whatever I was doing and let it operate in its normal sense, it's going to slide back to 327. It's going to find out where is the nearest steady state, which nearest steady state is from the direction of R and G. If R is greater than G, it's going to tend to cool down. It's going to get colder. So if I were to feed it anywhere all the way up to 442, let's say I fed it up at 441, right next to it. Which one's bigger, R of G, or R of T or G of T? It's still R, right? So even if you feed it right next to that central point, this is a steady operating state, right? I can satisfy the energy and material balances if I operate at 442. But if I get even right up to 441, if I don't get it right to 442, I'm always going to hit this point and then slide back to here. Because I'm always removing more energy than I'm generating if I'm on that side, if R is greater than G. So even if I operate up here, if I am initially up there, and I let the system run, it's going to slide back down this curve until I get to 327. What if I go above it? Over here, let's say this is 500. 500 is going to be somewhere like this. Now which one's bigger, R of T or G of T? G of T. So if I'm over here, I have G is greater than R. This is the equivalent to running around outside when it's really hot. You are generating energy at a faster rate than it can be removed by whatever you've jacketed your reactor with. Therefore, if you initially set the reactor of the temperature of the reactor up to 500 somehow, you hold a Bunsen burner under it or something, and temporarily get it up to 500, and then take the Bunsen burner away and let it operate normally, you're going to be in a situation that we've described there as 500. And now, which steady state are you going to head towards? Higher, right? You're going to go to 618, because now the rate at which you're giving off energy is higher than the rate at which it's being removed, and you're going to end up forcing yourself up both of these curves to that steady state. What if you fed it at 443? It's the same thing, right? Even if I'm at 443, G is still greater than R. Maybe it's not greater by as much as it was at 500, but it's still greater, which means the temperature is going to go up. What's that mean about the temperature in the middle, 442? It's what? You're in the direction, the word we would use is not ideal, it's not... You are at equilibrium at the center. Anybody got a bottle of water? I need to be able to throw it. We don't have a bottle of water. Okay, I'm going to use my pen. Imagine this pen can only move in one direction, right? I'm going to throw it like this. I wanted to do the little flipping water thing. Anyway, assume it can only move in this direction, right? It can't go this way and it can't go that way. Somehow it's in a little channel. I'm going to flip this pen over there. There's 3 different orientations it can take, right? One is like this. It's going to lay on the table with the cap going that direction. One is with the cap going this direction. What's the other one? Straight up. Would anyone like to take bets to see if I can get this to stand straight up? Probability, simply from throwing that thing back and forth, suggests it's either going to land this way or it's going to land this way. There is, however, a very slim chance that if everything winds up just perfect, if I have exactly the right conditions, we can get a third steady state. But it's not particularly stable, right? If somebody comes along and does this, it immediately falls back to one of those other 2 more stable systems. This is what that center point represents.
What if you were like starting at 442?
Exactly, right? If I can get the reactor in just the right way to operate exactly at 442, I will stay exactly at 442. But if it fluctuates even a little bit, if somebody comes by and kicks the thing and adds a little bit of energy to it, or you hold your hand on it and heat it up a little bit, or probably cool it down if that thing were a couple hundred Kelvin, you will probably cool it down and you will shift yourself off of that central steady state. This one is what we call unstable. It is real, right? I can operate there. I can balance a pen on its tip if I really want to. This one's a little bit easier because it's fat. I could do it maybe to that one if I wanted to. Oh, I had a pen right there. Why didn't I do that? It is possible to get there under the right conditions. But it's not very stable because if you bump it at all, it's going to shift to either the one at 327 or the one at 618. What happens if I come in above 618? It's going to shift down to 618, right? Because now if I'm on the upper side of 618, let me draw that as purple because that's the color I've been using. Right? If I go up here, now R is greater than T, and it's going to tend to cool back to those points. So the 2 other dots that we have are what are called stable. So I'm going to draw those as solid circles. I'm only going to label one, but they're, well, no, I'll label them both. These are the ones that you will probably operate at. This one or this one. It is possible to operate at the center, it's just pretty unlikely. And if you're there, it's going to cause you quite a bit of headache to stay right there. Doesn't mean you can't do it, but it's kind of unlikely.
Professor, would you call that like GOT stable or RLT stable, depending on the region?
Maybe. I'm not familiar with the terminology that works like that, but I don't see any reason why you couldn't say something like that. If you defined, you know, X stable meaning X as whichever one is higher, then sure. But if you go to the other side of the stable point, it flips. So if you could develop a convention, sure, you could call it something like that. How come 327 is also stable? Because if I go beyond this point, now I'm generating more energy than I'm removing, and I'm going to fall back to 327. So this one is stable because if you're on either side, you always hit only 327. Same thing for 618. But 442 isn't stable because if I'm not dead on 442, I'm going to go away from 442. So the last point that we have on something like, now that we have a very dirty plot on here, how do we decide which one that we operate at? Usually we can't change g of t. We assume that g of t is fixed. Why is g of t fixed? Because there's not really any knobs that we can adjust inside g of t, right? G of t is talking about FA naught times x times delta H. We could presumably change the flow rates a little bit, but for whatever reason, people typically don't do something like that because the rest of the system usually can't handle increased flow rates. Especially if it's a liquid, you run into the danger of making things blow up. So g of t is typically fixed. There's nothing in there that we can change in terms of operating the reactor. R of t, however, has a couple of variables that we can tweak. We can change R of t. The two variables that we can tweak in R of t are TA, so we can change the coolant temperature. Right? We can heat up the coolant or cool down the coolant, and we can shift TA. Or we can change the inlet temperature. Right? If I have a stream going into one of those reactors, maybe I hold a Bunsen burner in front of the inlet stream and temporarily raise that temperature. Either one of those is going to shift that R curve, the R of t curve. So this R of t that we've got, I'll label it over here. R of t, we can adjust either TA or TI naught. If we adjust R of t by changing either TI naught or TA, we're still going to have a straight line, right? It doesn't change the dependence of R on temperature. It's just changing where that line is. So this is what your homework is going to do. Your homework is plot this and make sure that you can identify where those points are. It should look something like this. Then replot R by changing TI naught. As you change TI naught, you'll see the only thing that's changing is where that R line locates. As you raise TI or lower TI, you're going to get either R to shift this way or R to shift this way. All right, you're just going to move R up and down on that curve. It's a little hard to see here because we've got so much stuff on there. It'll be easier if you actually have this in front of you and you can just fiddle with that TI naught. You'll see that that R curve is changing. What do we want to change it to? We want to change it to a point where we only have one steady state. If we were to operate a system under a particular set of conditions such that we only have one steady state, then that's the only one we operate at. Take a look at this blue curve. How many intersections are there of the blue curve with the red curve? There's only one, right? Up here. I tried to make those such that they're not touching. If you shift that R curve just enough to one side where you've only got one intersection, then you've only got one stable state, or one stable steady state, which is up there at the top. Once you're operating at that condition, now you can cool it back down to your original conditions, and you'll sit at that upper steady state. This is how we make the reactor perform at a particular conversion, is by initially changing something about either the inlet temperature or the coolant temperature in order to move that R curve around. You're going to develop the equations for R and G. Actually, I just gave you the equations for R and G. So that's something that you can try on your homework. And your goal on the homework is adjust TI naught until this blue curve is just far enough to the right that you've only got one intersection up there. What temperature TI naught do you need in order to do that? That's what you're trying to figure out in your homework. So I think I've gone a minute over. But it's quite a messy plot up there. I like it. So take a look at this plot when you're working on your homework and make sure that you understand why those states are stable. because there's almost guaranteed to be a question on a final where I say identify the stable state. Thank you all very much. Jenna's got a problem session this afternoon, and on Monday we'll start talking about some design principles of chemical reaction engineering.